Hello everyone, welcome to the Tim Booker channel. Wishing you a pleasant listening experience. Today, the book I'm going to talk about is A World Without Soil by American biologist Joe Handelsman. Handelsman is a heavyweight figure in the scientific community, renowned not only as an expert in soil microbiology but also as a member of the National Academy of Sciences in the United States. During Barack Obama's presidency, Handelsman served as the President's Science Advisor and Deputy Director for Technology in the White House Office of Science and Technology Policy. During his tenure in government, leveraging his expertise, Handelsman's primary responsibility was to provide consultation and advice on agricultural policy formulation for the U.S. government. He mentioned that, in order to fulfill this duty, he and his colleagues conducted numerous surveys in different agricultural regions across the United States, extensively reviewing reports on agriculture and soil conditions. However, these research efforts led to a startling conclusion: not only in the United States but globally, a crisis of soil erosion and degradation is underway. Without intervention, a global shortage of food and inevitable climate disasters will occur. Consequently, after leaving his government position, Handelsman felt compelled to write an educational book about soil, aiming to draw more attention to his findings and perspectives. This decision stemmed not only from the imminent soil crisis but also from his belief that the significance of soil for human survival and development has been overlooked. As a soil microbiologist, he felt a profound obligation to undertake the task of popularizing this knowledge. Therefore, at the outset of this book, Handelsman emotionally expressed that the reason for writing it is because the plight of soil has silently evolved into a global crisis. The land beneath our feet is eroding at an alarming rate, directly threatening the foundational aspects of human existence, food production and environmental safety. The purpose of this book is not only to educate about the immense contribution of soil to human survival and to reveal the threats facing the land but also to explore solutions. Furthermore, it aims to convey Handelsman's deep attachment to the earth. This seemingly inconspicuous material, spread across every corner of the globe, nurtures life and maintains its perpetual cycle. Next, I'll divide the discussion into 3 parts to elucidate the main content of this book. Firstly, let's delve into the origin of soil on Earth and its indispensable role in sustaining and evolving the entire ecological system. Moving on to the second part, we'll examine from the perspective of humankind the irreplaceable contribution soil has made to our survival and development, along with the genesis of this global soil crisis. Lastly, in the third part, I'll explore Handelsman's proposed solutions to this global soil crisis based on his narrative. In the beginning of this book, author Handelsman highlights the significance of soil to humanity through a small detail: both soil and earth in English are represented by the same word, earth. Soil is metaphorically depicted as Earth's dark layer, composed of minerals and biological molecules. Among the known universe, only Earth possesses this unique layer, nurturing the miracle of life on our planet. Under what fortuitous circumstances did soil emerge on this small blue planet of ours? Handelsman explains that 3 elements, rocks, water, and early life, are essential for soil formation. Earth has existed for about 4.55 billion years, and 150 million years after its formation, rocks and water were present. Subsequently, over 3 billion years ago, life, understood as self-changing and self-sustaining chemical systems, emerged in the oceans. Initially, simple RNA molecules capable of self-replication appeared, followed by simple single-celled organisms, composing the magnificent symphony of biological evolution on Earth. Though soil might seem unrelated to rocks in the eyes of ordinary people, rocks indeed constitute the primary raw material for soil production. Over countless years, rocks, whether due to thermal, mechanical, and chemical processes, heat caused rocks to expand and fracture. In sub-zero temperatures, liquid water froze, further fracturing the rocks. As more components of rocks were exposed to the air, remarkable transformations occurred. Limestone gradually dissolved in water, while some constituents reacted chemically with oxygen and other substances in the air, breaking down into smaller particles and fragments. For instance, silica, the fundamental material of sandstone, one of the most common rocks in the Earth's crust, disintegrates into the familiar grains of sand. These larger mineral particles create gaps allowing air and water to flow freely within the soil. Clay, the smallest particles in soil, is composed of hydrated silicate minerals, similar in size to bacteria, capable of absorbing various metal components. Between clay and sand, there exist medium-sized particles called silt, a mixture of minerals like quartz and feldspar from rocks. If soil were likened to a three-dimensional metropolis, these particles would represent buildings of varying dimensions, hosting a diverse array of microorganisms. Biologists estimate that globally, there are trillions upon trillions of bacterial species living in soil, numbering astonishingly in the billions within a teaspoon of soil. This abundance of bacteria quickly establishes a symbiotic relationship with the soil. It serves as their foundation for existence, while bacteria, through diverse biochemical reactions, transform the soil environment, paving the way for the birth of more complex life forms. After a rainfall, one might catch a whiff of a distinct earthy scent in the outdoors, a slightly pungent odor. The author explains that this unique, earthy smell arises from chemical substances released by bacteria in the soil, called geosmin. Although not pleasant to the nose, geosmin contains chemical elements essential for both microorganisms and macroscopic organisms. According to the author's research, 25% of documented species globally reside in the soil. In just 1 hectare of soil, the total biomass of inhabitants exceeds 1,500 kilograms, equivalent to the weight of 2 cows. Hence, scientists speculate that the appearance of soil around 3.5 billion years ago might be attributed to the tireless efforts of early organisms, particularly bacteria. How exactly do bacteria transform rock debris into soil on Earth? Some bacteria continuously excrete acidic substances to decompose minerals and acquire nutrients. Others convert atmospheric nitrogen dioxide into ammonia stored in the soil, providing essential nutrition for the birth and evolution of early plants. During cellular division and growth, inadequate nitrogen supply directly hampers the formation and growth of new cells, slowing down or halting plant growth. Nitrogen fertilizers, a significant category in artificial synthetic fertilizers used today, aid in robust crop growth and increased yields. Plants germinate from soil, evolving over the subsequent millennia. Conversely, they nourish the soil that nurtured them and sustains other organisms relying on it. Plant roots, through photosynthesis, input carbon fixed during photosynthesis into the soil, supplying vital nutrients for various microorganisms and larger surface-dwelling animals. The global carbon storage in soils is approximately 25 trillion tons, surpassing the total carbon emissions caused by human activities since the mid-18th century. Simultaneously, plants release substances like plant proteins and polysaccharides into the soil in a mucus form, binding soil particles into aggregates. Furthermore, when plants and animals die, microorganisms like bacteria and fungi decompose their remains, obtaining energy and injecting more nutrients into the soil. This perpetuates an unending energy cycle within Earth's terrestrial ecosystem. Part 2. Soil's condensed history in the immense contribution of the Earth's ecosystem discussed. Now let's shift focus to soil's profound role in human survival, civilization's evolution, and the soil crises we face today. Considering soil's contribution to humanity, one immediately thinks of it as the foundation of human agriculture and sustenance, dating back to the inception of human ancestors. Around 95% of human food is derived from the land. Nearly every early civilization's mythology featured a deity related to the earth or land, often represented as a female entity. This stems from the belief that working the land yielded regular, stable food supplies, equating the land's giving to a mother's selfless love and reproductive capabilities. Around 11,000 years ago, post the Earth's last ice age, a warming climate led to a proliferation of edible plants globally. Our ancestors discovered they could consciously gather seeds of these plants, sow them in soil, and reap regular harvests, marking the birth of agriculture. However, the yield varied based on the soil quality. Thus, since the inception of agriculture, enhancing or maintaining soil fertility became a primary concern. Early religions devised mystical rituals to pray for sustained soil fertility. Modern understanding attributes this to the levels of bacteria and fungi within soil, which meticulously recycle organic matter from deceased flora and fauna, enriching the soil. Higher microbial diversity in soil results in increased organic matter, offering more nutrients for various organisms and ensuring greater biodiversity. Visually, soils rich in organic matter tend to be black or deep brown, hence the term black soil becoming synonymous with fertile soil. The world's black soil belts mainly exist in the Eurasian central landmass from Ukraine through Russia to northeastern China, and two other regions in North and South America. Soil not only provides essential food but also hosts vital freshwater resources, i.e., groundwater. Groundwater constitutes 75% of the world's freshwater resources, with humans relying on it for 50% of drinking water and 40% of irrigation water. Furthermore, soil not only stores precious water but also cleanses and filters it, trapping harmful substances as it percolates deeper, thanks to soil particles and microorganisms. Moreover, soil microorganisms have quietly furnished humanity, especially since the industrial age, with many logistical necessities, from industrial fuels like oil and coal to life-saving antibiotics. However, after extolling soil's significance, Handelsman shifts gears to deliver alarming news: a severe global soil crisis has surreptitiously emerged. Without intervention, soil may fail in its 3-billion-year-old duty of supporting human and other earthly life. So, what's happened? Handelsman introduces a chilling term: soil erosion. Erosion, a neutral term in geological science, refers to natural forces like water currents moving soil particles elsewhere. Yet here, soil erosion signifies a human-induced environmental disaster. It's the loss of nutrient-rich topsoil in agriculturally developed regions globally. How grave is the situation? Handelsman asserts that the annual global soil loss reaches 36 billion tons, 10 to 30 times faster than soil regeneration rates. What have humans done to cause this soil crisis? The answer lies in upgraded agricultural techniques driven by population growth, expanded agricultural cultivation, and deforestation, among other factors. For instance, using metal plows allows deeper soil turnover for planting, optimizing soil nutrient use but severely compromising its structure, breaking up soil clumps, making them more susceptible to wind and water movement. Similarly, forest destruction renders soil more vulnerable to erosion. Forests effectively reduce wind speed and river flow, slowing their effect on soil. Tree roots buried in soil form an underground network anchoring it, while fungi attached to roots continuously release organic matter, maintaining soil nutrients. However, excessive deforestation disrupts this natural ecosystem. Handelsman exemplifies the Piedmont region stretching from New York to Alabama in the United States. Its topsoil is merely 6 to 10 centimeters thick, reliant on forest cover for ecological stability. However, since European settlers arrived in the early 18th century, vast forested areas were cleared for economic crops like cotton and tobacco. Soon, severe soil erosion occurred. Annual crops like cotton and tobacco, with shallow root systems, couldn't secure soil as effectively as trees or perennial plants. By the late 1960s, due to the loss of nutrient-rich topsoil, most agricultural production in the Piedmont ceased, leaving barren fields. Similar instances are happening globally. In traditional grain-producing regions of South Asia, half of the farmland degraded due to soil erosion, causing annual losses of up to $10 billion, equivalent to 2% of the GDP and 7% of agricultural output for the entire region. Likewise, aggressive grazing to bolster animal protein supply accelerates soil erosion. Overstocking agricultural livestock leads to excessive vegetation grazing, preventing regeneration. Frequent animal movement compacts soil, inhibiting water penetration, causing rapid desiccation and desertification, unsuitable for grazing or cultivation. Continuous soil loss directly results in reduced agricultural yields, plunging farmers into poverty, especially in developing nations. Handelsman estimates that if global soil erosion continues at the current rate, by 2050, global crop production will decline by at least 10%, sparking an unprecedented global food crisis. Worse, soil erosion could lead to frequent extreme climatic events, creating a vicious cycle: extreme weather causing soil erosion, while intensified erosion exacerbates extreme weather. Why does soil loss lead to extreme climate? Soil contains abundant carbon. Intense soil erosion causes a massive carbon leak from this reservoir, converting a portion into greenhouse gases like methane, carbon dioxide, and nitrous oxide, entering the atmosphere. More greenhouse gases imply more trapped heat in the atmosphere, resulting in a significant rise in global temperatures. Since the industrial era, the global average temperature has risen by a full degree Celsius. If it reaches 1.5 degrees Celsius, severe climate disasters will ensue. Some areas are already on the verge of collapse. For instance, the Arctic experiences twice the pace of temperature rise compared to other regions. Melting polar ice caps raise sea levels, displacing numerous species, while warming seawater accelerates marine life extinction, affecting both natural coral reefs and aquaculture. Furthermore, drastic temperature rises lead to more natural disasters, superstorms, heat waves, earthquakes, droughts, and tsunamis. Increased soil moisture evaporating into the atmosphere leads to heavy rainfall. Higher atmospheric and ocean temperatures make tropical storms more prevalent, escalating them into devastating hurricanes. Extreme climates also indirectly affect human survival by influencing other organisms. For instance, high temperatures alter behavior in many virus-carrying organisms, causing them to leave their habitats, as seen in the deadly coffee leaf rust disease that ravaged the global coffee industry. This fungal plant disease was once confined to Southeast Asia due to strict quarantine and its aversion to cold. However, with strengthened global economic ties and rising temperatures, it spread to major coffee-producing areas in South America in the 1970s, forcing plantation migration to higher, colder altitudes to escape the disease. Similarly, in 1989, northwest Venezuela faced a hemorrhagic fever outbreak. The culprits were local rodents, cotton and cane rats, driven from their habitats due to excessive human agricultural expansion and rising temperatures. They carried a lethal virus, posing no harm to the rodents but leaving humans defenseless against their immune systems. Part 3. So, faced with such a serious and imminent soil crisis, what can humanity do? The surefire approach is to find ways to reduce soil erosion and improve soil quality. The author suggests that, to achieve this goal, sometimes we need to look back and draw inspiration from ancient traditional agricultural techniques. For instance, in the northern Atlantic on Scotland's native land, there's an ancient archipelago called the Shetland Islands. For over a millennium, the residents here have been managing the soil in the same traditional manner, using spades instead of plows to till the land and fertilizing it not with chemicals but with a mixture of manure, grass, seaweed, and cowshed bedding, a traditional compost. Calculations show that the fertile topsoil layer on the Shetland Islands reaches a staggering 75 centimeters thick in farmland, 5 times thicker than the uncultivated surrounding soil. Next, the author takes us to the tropical rainforests from Mexico to the Guatemala border. Here, a small tribe called Lacandon, direct descendants of the Central American Mayans, resides. Handelsman mentions that while there's a prevailing belief that the collapse of the ancient Mayan civilization was due to their backward agricultural techniques, recent studies suggest otherwise. The agricultural methods once ridiculed might still have relevance today. Even today, the Lacandon people continue to employ their ancestors' agricultural practices known as the milpa system. On a single piece of land, they intercrop dozens of crops such as corn, squash, and beans. This provides the Lacandon people not only with a diverse range of food but also ensures the soil's microbial diversity. After 4 years, when soil fertility diminishes, the Lacandon start planting various trees among the crops, producing fruits, cocoa, medicinal plants, and more. Simultaneously, the roots of these trees firmly anchor the soil, preventing it from being washed away by storms or rainfall. Periodically, during the farming off-season, the Lacandon cut down aging trees, burn them, and use the nutrient-rich ash to rejuvenate the soil. Lastly, Handelsman introduces us to the ancient Indian tribe of the Zuni people in Colorado, USA. The Zuni are experts in soil conservation and irrigation. Due to being in a semi-desert dry area, their only dependable water source is rivers from nearby mountains. Therefore, the Zuni's farmland is typically located at the valley bottoms or plains near the foot of the mountains. However, the river water from the peaks, rich in organic sediments ideal for crop growth, during the high water period can cause severe soil erosion, damaging growing crops. What did the Zuni do? They ingeniously constructed a complex system of diversion and water retention using various materials. These include small stone-built dams, zigzagging diversion weirs, earthen embankments made of sand, and small ponds built with cobblestones scattered throughout the fields, known to agricultural scientists as zuni bowls. All these facilities aim to slow down and redirect the rushing river water, ensuring a precise balance, enough for the soil to absorb adequate moisture and accumulate natural organic material from the river, yet preventing it from carrying away the topsoil in the fields. This is something that large-scale dams created by modern engineering cannot achieve. After presenting these case studies, Handelsman concludes that although these seemingly primitive traditional agricultural production methods lag far behind modern agriculture in terms of yield, efficiency, and scalability, they embody three key points crucial to reversing the global soil crisis: diversification of cultivation, soil conservation, and effective soil fertility management. Of course, learning from these experiences does not entirely negate the effective technological and large-scale agricultural practices since the Industrial Revolution, but rather advocates for their integration. For instance, the increasingly popular no-till technology globally. This technique, essentially, involves directly seeding after the previous crop's mature harvest. Its advantages lie in avoiding the extinction of soil microorganisms caused by deep plowing, reducing the probability of soil fragmentation, lowering the chances of soil erosion, and maintaining soil absorbency. Since the 1940s to the 1960s, this new cultivation pattern has gradually mechanized, utilizing automated farm machinery such as no-till seeders, with production efficiency matching or even surpassing traditional deep plowing. A farmer named Bragg from Wisconsin, USA, tells Handelsman that due to adopting no-till seeding technology, even in heavy rain, his farmland experiences minimal soil erosion, with most rainfall effectively absorbed by the fields. Apart from no-till technology, another agricultural solution to slow soil erosion is farmer-managed natural regeneration, FMNR, particularly suitable for developing region farmers with limited resources and small plots of land. The core concept of FMNR is somewhat akin to the MILPA system mentioned earlier. In essence, it involves farmers utilizing native trees near their residences, like shrubs, by watering, branch planting, regular pruning, and burning excess branches into natural fertilizers, thus creating a sparse forest. This helps the root systems fix the soil and restore soil fertility. Subsequently, farmers utilize the land within the forest for both crop cultivation and ancillary activities such as beekeeping, fruit tree planting, and livestock development. Bees aid in pollinating fruit trees, increasing fruit yields, while the honey can be sold for income. The livestock waste, mixed with tree leaves and wood ash, becomes excellent natural fertilizer. Handelsman's investigation pleasantly discovers that in Niger, the widespread adoption of FMNR has increased annual grain production by 500,000 tons, enough to feed 2.5 million people, with each household's average annual income rising by 11%. The resultant improvement in soil quality and climate, however, cannot be measured in monetary terms. Handelsman also proposes that urban agriculture using rooftop spaces and idle land, along with soilless hydroponic cultivation, can mitigate global soil erosion and the food crisis caused by extreme climates to varying extents, serving as complementary solutions. Nevertheless, due to the universal and severe nature of the global soil crisis, objectively, it still requires an international cooperative framework and a comprehensive set of solutions to coordinate actions. In his book, Handelsman emphasizes that the COVID-19 pandemic has shown a glimmer of hope. It demonstrates that in the face of a widespread crisis, the entire world can still unite and implement rapid collective action. However, existing cooperation agreements, including the United Nations Food and Agriculture Organization's World Soil Charter, lack a specific international cooperation body and an accountability mechanism. Therefore, Handelsman suggests using the 2015 Paris Climate Agreement as a basis to derive a draft specifically for agricultural land. For example, by improving soil quality, allowing for an annual global agricultural land carbon sequestration increase of 400 million to 1 billion tons, this would provide robust support for the global greenhouse gas reduction outlined in the Paris Agreement. On this basis, the United Nations Climate Change Conference should establish a specialized organization involving participation from various countries to formulate carbon sequestration indicators for each country's agricultural land. Nevertheless, this goal is just the first step of a long journey. Alright, I'll be introducing the main content of A World Without Soil to you here. In this book, author Handelsman has been concise, providing us with three major sections about the origins of soil on Earth, the indispensable role of soil in human survival, development, and the entire ecosystem, the serious soil crisis facing humanity today, and some potential solutions. It's like a mini encyclopedia of soil, all packed into a brief read. Handelsman shares in this book that soil could be termed the dark matter of the Earth's surface, essential yet seldom noticed, taken for granted by humans and all living beings relying on it. Since the Industrial Revolution, as agriculture has shifted toward mechanization, intensification, and the use of fertilizers, land has increasingly provided us with bountiful food. However, this agricultural revolution has also been a significant driver of a global soil crisis, meeting the growing food demands of the global population by overexploiting the future potential of land. Towards the end of the book, Handelsman urges that to salvage this soil crisis, it requires not only concerted efforts from international organizations and governments worldwide but also a revolutionary change in agricultural production. Furthermore, it necessitates a global societal shift from past neglect and apathy towards comprehensive attention to soil degradation. For instance, international and national financial institutions should subsidize farmers practicing healthy agricultural production methods that reduce carbon emissions. Similarly, cultural, entertainment, and educational institutions should continue to advocate, raising awareness that safeguarding soil, reducing carbon emissions and plastic pollution are as crucial and urgent as global peace issues. While Handelsman admits that so far, neither himself nor colleagues in the scientific community have discovered an effective, singular, and rapid solution to halt this increasingly severe soil crisis, he remains optimistic about the future. After all, with action initiated, the amalgamation of human intelligence and the soil's ancient yet resilient regenerative capabilities can overcome any challenge. That sums up the essence of this book. Congratulations on completing another book. Thank you all for your support and attention. Please subscribe to the Tim Booker channel, like, and share this valuable knowledge with your friends. Let's combine wisdom and practice to achieve our financial goals and create a better future together. Thank you, goodbye.